There's one thing we can do with any derivative that is often very handy when you're in situations where you have limited information. And what I mean by limited information is this kind of situation. So suppose we have a population of flies. Maybe we're doing some biology, some genetic experiment on flies or something. And we have a population of 1,000 individuals. And we know from past observations that under current environmental conditions, the size of the population will grow at about 10 individuals per day. Let's approximate how large the population would be after 3 days. Now, the thing is, over these 3 days, the environmental situation might change, and so this rate of change might not be constant. So we can't just multiply this 10 by 3 and say that we'll have 1,030 individuals, because this rate of change might not be constant. So in general, right, we have some population that's a function of time. And who knows what the graph of that looks like. Maybe it's like this. And maybe this is the time that we're talking about. Okay. So the derivative, so there's this unknown population function, p of t. And it has a derivative. Right? Let's call this time t naught. It has a derivative, and the derivative tells you the slope of the tangent line. So if we wanted to, we could find this tangent line. Now we're asking what happens 3 days later. That's going to be over here at t naught plus 3. And you can see that the amount that the function has gone up is this green segment here. But because we don't have a formula for the function p of t, we can't actually find how big this green segment is. We just don't have enough information. But what about the tangent line? Well, the tangent line goes up by this yellow amount right here, which isn't the same as the green amount. You can see that it's smaller, right? But as long as we don't go too far off into the future, these two values, the change in the tangent line and the change in the function, shouldn't get too far apart. So the idea here is that if our change in time is small, then the change in the tangent line is going to be approximately the same as the change in the function, which is p of t. Okay, so what is the change in the function? Well, I guess we would call that delta p. And what about the change in the tangent line? Well, we know the slope of the tangent line. It's the derivative of p at t naught, which is now. Okay, and the change of the tangent line, that's this yellow line segment here. We know that this change in time is 3. Oops. So we know the slope of this red line. We know this horizontal distance is 3. But this vertical distance, right, we have this right triangle here. We have this line with a change horizontally and a change vertically. We know that in this situation, we know that this slope is the rise caused by moving over some amount. And we're trying to find this rise. So it's not clear what to call this. What we're actually going to call this is dp. So this slope is p prime. This rise is dp. And the run is delta t, which is 3. We'll plug that in later. And we wanted to know dp, right? That's what we're looking for. So let's just multiply both sides by delta t. We get dp equals p prime of at t naught times delta t. Now we can plug in everything we know. So we know that, right, we're using the value of this derivative at t naught, and that's 10. And then delta t is 3. So what we get here is 30 individuals. And that's dp, but that's approximately the change in the population. So the total population after 3 days is going to be approximately the population we started with, which is 1,000, plus the change in population, which is approximately 30. So 1,030. Now, probably that's what you would have come up with if we didn't go through all of this calculation. But the idea here is that this is something we can use in general. So in general, if you ever want to know how much a function has changed, you can take the derivative at the starting value and multiply it by the change in x. And I shouldn't write equals here. This is an approximation, so these won't be equal in general, but as long as delta x is small, we can approximate any change in a function by multiplying its derivative at our starting point by the amount that we're changing x.